solar battery in solar energy system, understand the need to check the condition of electrolyte in a solar battery, identify with the instrument needed to measure electrolyte of a battery, and understand why it is necessary to monitor the electrolyte in solar batteries. Solar energy is one of the renewable and reliable energy sources which can meet the energy demand of future to greater extent. Solar batteries store the excess energy generated by your solar panels, which can then be used to power your home during gloomy, rainy days or after the sun sets. When solar energy is pumped into a battery, a chemical reaction among the battery components stores the energy. The reaction is reversed when the battery is discharged, allowing current to exit the battery. Solar batteries increase the reliability of solar power systems and decrease dependence on the conventional power grid. The ability to store and utilize solar energy even during periods of limited sunlight makes solar power a more practical and efficient choice for renewable energy. Several factors affect the performance of the solar battery. They are type or material, battery life, depth of discharge, and efficiency. The four main types of batteries used in the solar power are lead acid, lithium ion, nickel cadmium, and flow batteries. Among the four, lead acid batteries and lithium ion are commonly used. Lead acid batteries are used in automotive and industrial applications. They have a low energy density but remain both cost-effective and reliable. While lithium-ion batteries have a high energy density and offer a smaller, lighter, and more efficient option, they allow the user to access more of the energy stored within the battery. Solar batteries require regular and careful maintenance for a longer battery life. Battery life can be extended if it is kept at high state of charge, not over-discharged, or operated at excessive temperatures over 35 degrees Celsius. Properly maintained battery state of charge is key to maximizing battery life. A very low state of charge implies that less electricity energy is stored in the battery. The longer the period of low state of charge, greater the chance of sulfation buildup on the plates. This results into shorter battery life. Shown here is a hydrometer that is used to determine the density of a liquid. It usually consists of a glass float with a long thin stem which is graduated. The glass float is a large hollow bulb which increases the buoyancy so that the hydrometer floats. The narrow stem increases the sensitivity of the hydrometer. The bottom of the hydrometer is made heavier by loading it with lead shots so that it floats vertically. A hydrometer is used to measure the concentration of sulfuric acid, specific gravity of battery electrolyte, battery acid. You can easily and accurately determine a non-sealed battery's state of charge. It sinks less in a denser liquid and more in a lighter liquid. The lowest density is marked on the top of the stem of a hydrometer, and the maximum density is marked at the bottom of the graduated stem. Please note to check the electrolyte level and to ensure that it is above the plates in all cells. If it is below the plates, the test cannot be carried out until water is added and the battery is charged to mix the water and residual acid in the battery. It is important to ensure that the plates do not remain exposed to air and are allowed to dry and oxidize. The procedure to be followed to check electrolyte in solar battery and add distilled water is as follows. Ensure you have all the following tools and equipment: hand gloves, hydrometer, distilled water and lead acid battery. Submerge the lower end of the glass tube, which is connected with a narrow tube made of acid resistant material, in the acid which is in the accumulator. Press the rubber bulb so that the air inside escapes from the narrow tube at the other end of the glass tube. Observe that as the pressure is removed, there is a partial vacuum in the glass tube and the acid pushes up into the glass tube. Now the hydrometer floats in the acid. Read the density of the acid on the floating hydrometer. Make observation based on the reading. Please note, the acid in a fully charged cell should have a relative density of 1.25 to 1.30. A reading of less than 1.18 indicates that recharging is necessary. Remove the surface charge if the battery has been charged within the last 4 hours. Remember, if the battery has been discharged within the last 15 minutes, wait for at least 15 more minutes before testing it. Squeeze the rubber bulb to release the electrolyte back into the battery cell. To increase the accuracy of the measurement, in the same cell, repeat this process several times so that the float will reach the same temperature as the electrolyte. At eye level and with the float steady, read the specific gravity at the point the surface of the electrolyte crosses the float marking. Release the electrolyte back into the cell from which it was taken. Be sure to avoid spillage and thoroughly rinse the hydrometer with water after using it. Here are some do's and don'ts of adding distilled water to the electrolyte. Only add distilled water to the electrolyte. Do not add acid. Do not add water with impurities, as these impurities will accumulate over time and will cause problems. Do not take a specific gravity (SG) reading just after topping up with water.
We have reached the end of this session on how to check the condition of electrolyte in a solar battery using hydrometer and adding distilled water to the required level in the solar battery. By now, you should be able to describe the role of solar battery in solar energy system, understand the need to check the condition of electrolyte in a solar battery, identify with the instrument needed to measure electrolyte of a battery, and understand why it is necessary to monitor the electrolyte in solar batteries. In this session, we will learn to remove complete electrolytes from a lead acid battery and refill. At the end of this session, you will be able to describe the importance of battery maintenance, explain the relationship between electrolyte quantity and charge storage capacity, and describe the steps in draining and refilling electrolyte in the battery.
Battery maintenance is well recognized as an important part of running an efficient and safe warehouse. However, the appropriate procedure for battery maintenance is often overlooked. Performing maintenance in the correct order is just as essential as the maintenance steps when it comes to saving time, extending the lifespan of your battery, and protecting your equipment. Moreover, establishing the appropriate procedure for battery maintenance is a vital part of maintaining a productive and safe work environment. Charts and maintenance schedules are a good way to ensure that batteries receive the appropriate maintenance. Let's briefly go through common defects in batteries. There are short-circuited cells due to failure of the separator between the positive and negative plates, short-circuited cell or cells due to a buildup of shed plate material below the plates, sulfation after a long period of disuse in a low or no charge state, corrosion or damage to the positive and negative terminals, broken internal connections because of corrosion, broken plates due to corrosion and vibration, damage to the battery case, and low electrolyte level. In the next section, you will see the relationship between electrolyte quantity and charge storage capacity. The charge storage capacity is the total amount of electricity a battery can store. You may have seen that lithium battery storage capacity is described in mAh or milliamp hour rating, and in the case of lead acid battery, it is amp hour. This charge storage capacity is highly dependable on the electrolyte quantity or active material and the plate's size. The electrolyte is water and sulfuric acid. Maintaining the appropriate electrolyte quantity is essential to facilitate the chemical reactions, charging and discharging. Insufficient electrolyte quantity reduces the battery performance and causes battery sulfation. Here comes the procedure to remove electrolyte from a lead acid battery and refill. Ensure you have all the following tools and equipment: rubber siphon, glass beaker, funnel, hydrometer, diluted sulfuric acid and lead acid battery 12 volts 100 ampere per hour. Wear hand gloves. Using rubber siphon, drain out electrolyte from the battery kept at higher level to the glass beaker and the glass beaker at the lower level. After emptying, check the anodes and cathodes for any cleaning requirement. Use light grade emery sheets and scrub the electrodes. Reinsert them. Using a funnel, pour the diluted sulfuric acid inside the battery till the electrodes get fully immersed. Check the density. If the density is higher, add distilled water to get the right specific gravity. Finally, record your observations. Please note, all personnel working with batteries should first be trained in the proper lifting and handling procedures. Also, it is a good practice to regularly remind workers of appropriate battery handling procedures to maintain a safe working environment.
We have reached the end of this session on to remove complete electrolyte from a lead acid battery and refill. By now, you should be able to describe the importance of battery maintenance, explain the relationship between electrolyte quantity and charge storage capacity, and describe the steps in draining and refilling electrolyte in the battery. Hi trainees! In this session, we will learn to connect the PWM controller with solar panel and solar battery and note input or output current and battery voltage at different time intervals. At the end of this session, you will be able to recognize the need and types of charge controller, explain the role of PWM controller in controlling power of solar panel and solar battery, and describe the steps in connecting the PWM controller with solar panel and solar battery to record current and voltage.
A charge controller is basically a voltage and or current regulator to keep batteries gets charged and prevent from overcharging. It regulates the voltage and current coming from the solar panels and going to the battery. The solar charge controllers are necessary for most solar power system that uses batteries. It controls the power as it moves from the solar panels to batteries. If overcharged, the life of battery is reduced. The solar charge controller performs the following major functions. It charges the battery, gives an indication when battery is fully charged, connects or disconnects the load, monitors the battery voltage, and when it is minimum, disconnects the load, connects or disconnects solar panel to circuit, protects the battery from overcharging, prevents battery from deep discharge, monitors the reverse current flow and block, indicates for charging on, battery connect, solar on, etc. Please note that the commercial charge controllers have 10 ampere to 40 ampere of charging current. Basically, there are three types of charge controller, namely on or off type controller, pulse width modulation, and maximum power point tracking. Let's see the role of PWM controller in controlling power of solar panel and solar battery. In PWM controller, when desired battery voltage is reached, output turns on or off quite rapidly. The battery voltage held constant, producing a more fully charged battery. More charge controllers make use of pulse width modulation. This is a process in which, as the battery starts to reach a fully charged state, the amount of power being transferred to it gradually decreases. PWM extends the battery life even more as it decreases stress on battery. It can also keep batteries in a completely charged state or floating indefinitely. PWM chargers are more complex, but they tend to be more durable as they do not use any breakable mechanical connection. In short, a PWM controller can be thought of as an electronic switch between the solar panels and the battery. The switch is flicked on and off as needed, pulse width modulated to hold the battery voltage at the absorption voltage. The PWM modulates the sinusoidal waves required by certain loads in a way to meet the requirement of the load. Now let us understand the features of this controller. Higher reverse of battery capacity, prevention of heating and gasification, and suitability to smaller applications. Here comes the procedure to connect PWM controller with solar panel and solar output. Ensure you have all the following tools and equipment: solar panel of 75 watts, solar battery 12 volts 100 ampere per hour, connecting wires, PWM controller, voltmeter and ammeter. Connect the components as per diagram. Place the solar panel in sunlight. Test input-output voltages. Record your observations.
We have reached the end of this session on to connect the PWM controller with solar panel and solar battery, and note input or output current and battery voltage at different time intervals. By now, you should be able to recognize the need and types of charge controller, explain the role of PWM controller in controlling power of solar panel and solar battery, and describe the steps in connecting the PWM controller with solar panel and solar battery to record current and voltage. Hi trainees! In this session, we will learn to connect the MPPT controller with solar panel and solar battery and note input or output current and battery voltage at different time intervals. At the end of this session, you will be able to recognize the functions of MPPT charge controller, explain the features of MPPT charge controller in maximizing energy harvest from solar panels, understand the advantage of MPPT charge controller, and describe the steps in connecting the MPPT controller with solar panel and solar battery to record current and voltage.
Maximum Power Point Tracking or MPPT solar charge controller is a battery charger and load controller for standalone PV systems. It is the most recent type of solar charge controller. This is an electronic tracking system that continuously compares the battery charge level with the output of solar panel. It will then adjust the voltage and current to be applied to the battery, conserving the same power from the solar panel but charging the battery more efficiently. The controller prevents overcharge or deep discharge. It provides automatic load control for the external load connected to the controller board. This optimized battery charging process increases battery life, minimizes battery maintenance, and improves system performance. Let's see some of the features of MPPT Solar Charge Controller. MPPT provides PWM type battery voltage control and extracts all available power from the PV module. MPPT technology can increase charge current up to 30% or more compared to traditional charge controllers. This controller features a smart tracking algorithm that maximizes energy harvest from solar panels. Further, in modern inverters used in solar PV electrical system, 3 levels of charging required by the solar batteries are accomplished by MPPT charge controllers. They are bulk charging, absorption charging, and float charging. The advantage of MPPT is operating the photovoltaic modules to produce maximum power. It varies the electrical operating point of the modules and enables them to deliver maximum available power. The additional power harvested increases the current available for battery charging. MPPT uses a mechanical tracking system in conjunction, but the two systems are different. Compared to PWM controllers, MPPT charge controllers are more expensive, but their performance is significantly enhanced. Here comes the procedure to connect MPPT controller with solar panel and solar output. Make sure you have solar panel of 75 watts, solar battery 12 volts 100 ampere hour, connecting wires, MPPT controller, voltmeter and ammeter. Connect the components as per diagram. Place the solar panel in sunlight. Test input-output voltages and current. Record your observations.
We have reached the end of this session on to connect the MPPT controller with solar panel and solar battery and note input or output current and battery voltage at different time intervals. By now, you should be able to recognize the functions of MPPT charge controller, explain the features of MPPT charge controller in maximizing energy harvest from solar panels, understand the advantage of MPPT charge controller and describe the steps in connecting the MPPT controller with solar panel and solar battery to record current and voltage. Hi trainees! In this session, we will learn to compare the results of the solar PWM controller and solar MPPT controller. At the end of this session, you will be able to describe the significance of charge controller, explain the differences between PWM controller and MPPT controller, and compare the behavior of PWM and MPPT charge controllers.
As we discussed earlier, the solar charge controllers are necessary for most solar power system that uses batteries. The solar charge controller functions to control the power as it moves from the solar panels to batteries. If overcharged, the life of battery is reduced. The simple type of charge controller functions to monitor the battery voltage and opens the circuit to stop the charging process once the voltage reaches a certain level. Older charge controllers accomplished this with a mechanical relay. Let's see the differences between PWM controller and MPPT controller. With a PWM controller, the current is drawn out of the solar panel. When desired battery voltage is reached, output turns on or off quite rapidly. Battery voltage held constant, producing a more fully charged battery. Whereas with the MPPT controller, maximum current is drawn. Provides PWM type battery voltage control. PWM extends the battery life even more as it decreases stress on battery. It can also keep batteries in a completely charged state or floating indefinitely. PWM chargers are more complex, but they tend to be more durable as they do not use any breakable mechanical connection. In case of MPPT, the controller also prevents overcharge or deep discharge. It provides automatic load control for the external load connected to the controller board. This optimized battery charging process increases battery life, minimizes battery maintenance, and improves system performance. Besides the type, charge controllers are characterized by the current they can control and the voltage under which they can control it, generally 12, 24 or 48 volts, which is the voltage of the solar module or array. They also feature the operating temperature and efficiency, almost always above 95%. Most power controllers for 12 volts applications will control a maximum under 50 ampere. Generally, high power photovoltaic systems are based on higher voltages. Here comes the steps to compare the behavior of PWM and MPPT charge controllers. Ensure you have all equipment listed here. Required tools are 12 volt 5 ampere PWM solar charge controller 1 number, 12 or 24 volt 10 ampere PWM solar charge controller 1 number, and 12 volt 10 ampere MPPT charge controller 1 number. Keep the results of voltage and current readings taken for PWM and MPPT controllers in previous procedures ready. Take the charge controller and look for label on it, usually at the back side. Compare and write your comments in the table. Write down the conclusion based on the observation.
We have reached the end of this session on to compare the results of the solar PWM controller and solar MPPT controller. By now, you should be able to describe the significance of charge controller, explain the differences between PWM controller and MPPT controller, and compare the behavior of PWM and MPPT charge controllers. Hi trainees! In this session, we will learn to open PWM and MPPT charge controllers and identify components wired to understand mechanism. At the end of this session, you will be able to know the general components of a charge controller, explain the components of PWM charge controller, explain the components of MPPT charge controller, and appraise the assembly of components inside a PWM and MPPT charge controllers.
Let's begin by restating about solar charge controller. The solar street lights use photovoltaic modules to convert sunlight into DC electric charge and use a solar charge controller to store DC in the batteries and automatically switch on street light in the evening after sunset. In short, a solar charge controller is used to charge the battery from power generated by solar panels and prevent the battery from overcharging. It is also known as a voltage or current controller as it directs the voltage and current from the solar panels to the battery and stops the reverse flow at night. Home systems use PV module for household applications in which charge controller plays important role. Shown here is the charge controller and its connections with other components in solar PV electrical system. Let's see the general components of a charge controller. It has two battery input terminals, two solar panel input terminals, and two load terminals. The load terminals are for running various DC loads like lights or our solar grid tie inverters. The external components of PWM charge controller are LCD screen, USB output, input terminals, injection port, plastic shell and iron backplate. Here is the PCB of PWM charge controller. The components are Arduino Nano, P MOSFET, power diode, buck converter, temperature sensor, current sensor, TVS diode, transistors, resistors, ceramic capacitors, LCD, RGB LED, bicolor LED, jumper wires or wires, header pins, heat sinks, fuse holder and fuses, push button, screw terminals, PCB standoffs, and USB socket. The components of MPPT charge controller are LT3652 driver, capacitors 2 pieces, green LED, orange LED, 220K resistor, 330K resistor, 200K resistor, 68 UH inductor, 1 UF capacitor, 100 UF capacitor 2 pieces, battery 7.4V, 1K resistors 2 pieces and barrel socket. Let's open the PWM controller. Required tools are PWM controller and screwdriver. To open the PWM controller, follow the steps shown here. Identify components wired to understand mechanism. Let's open the MPPT controller. Required tools are MPPT controller and screwdriver. To open the MPPT controller, follow the steps shown here. Identify components wired to understand mechanism. Compare the PCB, components, circuit, etc. and write your observations.
We have reached the end of this session on to open PWM and MPPT charge controllers and identify components wired to understand mechanism. By now, you should be able to know the general components of a charge controller, explain the components of PWM charge controller, explain the components of MPPT charge controller, and appraise the assembly of components inside a PWM and MPPT charge controllers. Hello trainees, welcome. In this session, we will be learning how to connect solar panel to an array junction box. At the end of this session, you will be able to describe the integrated components of Solar Power Conditioning Unit (PCU), understand the operational principles of a PCU, know the array mount inverters and the challenges associated with it, and explore the rooftop mounting mechanisms and influence the decision-making process for the installers.
A solar charge controller, an inverter, and a grid charger are the components of an integrated system called a Solar Power Conditioning Unit (PCU). It offers the option to use a grid or DG set or a solar power source to charge the battery bank. The load, solar power output, and battery voltage are all continuously monitored by the PCU. Owing to continuous power consumption, the PCU will automatically switch the load to grid or DG power and initiate simultaneous charging if the battery voltage drops below a predetermined threshold. The PCU always prioritizes solar power and only turns to grid or DG power when solar power or a battery charger is not sufficient to meet the load requirement. It acts as a reliable backup by seamlessly transferring to grid or DG power when needed, thus ensuring uninterrupted power supply. It is designed for user convenience with automated functions to ensure hassle-free operations. PCU promotes energy independence by harnessing solar power and minimizing dependency on conventional power sources. It contributes to a greener environment by promoting the use of clean, renewable energy from solar sources. It offers a reliable and redundant power solution by combining solar and grid or DG power sources for continuous operation. Solar Power Conditioning Unit (PCU) should be a powerful hybrid solar inverter with advanced maximum power point tracking, MPPT technology-based solar charge controller, digital display, and purely safe from short circuits. Heavy load handling solar PCU shall be an industrial design, heavily built for running power load such as 2 air conditioners and lighting load such as fans, lights, computers, printers, Xerox machines used in home, office, and commercial space. It should have conversion efficiency up to 97% through MPPT technology and connect solar panels up to rated kilowatt. It should give pure sine wave output and have multiple MCBs protection for safety to connected load. We can select the solar PCUs based on descriptions in the product manual such as capacity kW, technology sine wave MPPT etc., allowed power load, batteries requirement, solar panel voltage VOC, solar panel current, full battery recharge time, inverter monitoring displays namely LED display and LCD display for customer-friendly monitoring systems, etc. Let us now learn about the specifications of a solar PCU. The LED display may have grid LED green, that means grid power is available. PV LED green, that means solar is available. Inverter LED green, that means inverter is switched on. Battery LED, that means battery charging. Blinking or battery discharging. LED steady. Fault LED red, that means inverter is faulty. The LCD display may have battery voltage, that means charge level of battery. Load percent, that means power consumption as a percent of total inverter power. Output voltage. PV voltage, that means solar panel generating voltage. PV current, that means solar panel generating power in amps. Grid voltage, that means utility grid voltage level. Grid charging current, that means amp with which battery is being charged. Electricity saved, that means kWh. Wall mount or array mount inverter. For commercial rooftop solar installations, an inside climate controlled lockable room is the best location for string inverters, although that isn't always possible. Installers frequently place these delicate power electronics on the rooftop next to the array in situations when there are few options for ground level placement. Inverters mounted on rooftops are as follows: string inverters, central inverters, and micro inverters. Open the array junction box AJB and understand the inside features. Ensure you have all the following tools and equipment: array junction box AJB or combiner box, solar panels, wires, cables, tools, multimeter and open PCB assembled with components meant for PWM and MPPT charge controllers. Verify the circuit diagram and compare. Draw wires from solar panels and connect to input connector in AJB. Connect the input connector in series. Connect the fuse, DC, MCV and surge protectors. Connect the output circuit. Test the output voltage and current using multimeter. Remove the above connections and repeat for parallel connection. To make a parallel connection, remove the connections mentioned above and repeat. Try connecting inside AJB for series or parallel connection for solar panels.
We have reached the end of this session on Connect Solar Panel to an Array Junction Box. By now, you should be able to describe the integrated components of Solar Power Conditioning Unit (PCU), understand the operational principles of a PCU, know the array mount inverters and the challenges associated with it, and describe the rooftop mounting mechanisms and influence the decision-making process for the installers. In this session, we'll be learning how to connect and test a 12-volt DC or 230-volt AC normal inverter. At the end of this session, you'll be able to explain the primary functions for a solar and a normal inverter, describe the features of a normal inverter, understand the sequence for turning on a solar PV system, and know the step-by-step shutdown process for a solar PV system.
A solar inverter or PV inverter converts the variable direct current DC output of a photovoltaic PV solar panel into a utility frequency alternating current AC, a commercial electrical grid or used by a local off-grid electrical network. It is a critical component in a photovoltaic system, allowing the use of ordinary commercial appliances. Solar inverters have special functions adapted for use with photovoltaic arrays, including maximum power point tracking and anti-islanding protection. The front panel has power on or off switch, LED indicators for AC mains, solar on battery, normal load, overload, low battery, etc. The back panel has AC adapter jack, solar DC input terminals, battery input terminals, AC out socket, overload MCB, fuse, exhaust fan, etc. Let us now learn about the inverters in general. An inverter is an electrical device which accepts electrical current in the form of direct current DC and converts it to alternating current AC. For solar energy systems, this means the DC current from the solar array is fed through an inverter which converts it to AC. This conversion is necessary to operate most electric devices or interface with the electrical grid. Inverters are important for almost all solar energy systems and are typically the most expensive component after the solar panels themselves. Based on the necessity in solar PV electrical system, Different types of inverters are in use. Quite often, the type of inverter used helps in naming the type of solar PV electrical system itself. Accordingly, we have standalone SPV system, hybrid system, grid-tied SPV system and grid interactive SPV system in use. Normally, switching on the solar inverter, hence a solar PV system, is to be done in a sequence. Switch on DC isolator first, followed by AC isolator, followed by solar supply main switch. While shutting down, switch off solar supply main switch first, followed by solar AC isolator, disconnect, then by PV array and DC isolator, disconnect, and then inverter isolator, disconnect. The solar PV system should now be completely switched off. All lights and screen displays will be dead. Keep the system off for a minimum of 5 minutes before you restart. Shutdown system. Turn off the main DC battery isolator. Turn off the solar array AC main switch located in the switchboard or next to the inverter. In case you have two AC switches, both have to be shut down. Turn off the solar array DC main switch located next to the inverter. Please also check the shutdown procedure on the main switchboard. Turn on the solar array DC main switch located next to the inverter. Turn on solar array AC main switch located in the switchboard and or next to the inverter. Turn on the main DC battery isolator. To confirm the operation of the system, check inverter display while full sun is shining on the panels. The required tools are 12 volt DC or 230 volt AC normal inverter, load, 12 volt 100 ampere hour battery, connecting wires and clamp meter. Study the inverter for input and output connections. Connect the load bank to the output socket. Connect the solar battery 12 volt 100 ampere hour to the battery input connectors. Connect the mains cord to the AC mains socket. Switch on the mains and the inverter. Check the normal functioning of the inverter. Add load and measure load current. Add load little more than maximum overload and verify that overload alert and trip occurs. Remove overload and reset inverter. In normal load conditions, retain on state of inverter and switch off the AC mains. Verify the functioning of inverter on battery mode. Measure current drawn from battery using clamp meter. Verify the backup time on battery mode to function for at least 80%. Switch on AC mains and verify the inverter resumes function on mains. Disconnect the load. Switch off the inverter. Switch off the AC mains. Record the observations. Observations. An inverter is a device that converts battery power DC into alternating current AC of a higher voltage. A solar inverter's purpose is to convert the direct current DC electricity that is generated from a photovoltaic panel into an alternating current AC that can be used by in-home appliances and the community electricity grid.
We have reached the end of this session on connect and test a 12 volt DC or 230 volt AC normal inverter. By now, you should be able to explain the primary functions for a solar and a normal inverter, describe the features of a normal inverter, understand the sequence for turning on a solar PV system, and know the step-by-step shutdown process for a solar PV system. In this session, we'll be learning how to connect a solar panel 10 watts, solar charge controller 12 volts 10 ampere, solar battery 12 volts 100 ampere hours and a normal inverter and convert to a solar inverter. At the end of this session, you will be able to understand the fundamental principles and components of a solar panel, define the role and importance of inverters in solar energy systems, including their function of converting direct current DC from solar arrays to alternating current AC. Describe different types of inverters and their usages and understand the critical factors contributing to the success of solar PV integration projects.
Let us learn about solar panel firstly. A solar panel consists of many solar cells with semiconductor properties encapsulated within a material to protect it from the environment. These properties enable the cell to capture light, or more specifically, the photons from the sun, and convert their energy into useful electricity through a process called the photovoltaic effect. An inverter is an electrical device which accepts electrical current in the form of direct current DC and converts it to alternating current AC. For solar energy systems, this means the DC current from the solar array is fed through an inverter which converts it to AC. This conversion is necessary to operate most electric devices or interface with the electrical grid. Inverters are important for almost all solar energy systems and are typically the most expensive component after the solar panels themselves. Firstly, let us learn about standalone SPV system. Standalone SPV system is normally preferred in places where electricity is not available. Hence, it is suitable for remote areas, land or water bodies where grid supply is not available. Examples: border military service camps, naval services, farmhouses, mountains, forests, resorts, etc. The main components include battery backup and inverter. An AC main from grid is not used. Solar energy, the only source, is used to charge the battery bank and day lighting. During night, battery provides the energy input to inverter. Loads are normal AC loads and can be any. DC loads also can be used after charge controller. No AC output when battery bank voltage goes below its designed value. When we add an option of additional source of charging to the standalone solar PV system, we get the hybrid inverter based SPV system. Solar energy is the main source for charging the battery. Additional energy requirement is supplemented by AC mains. An auxiliary charging circuit helps charge the battery in the absence of solar energy. In the absence of sunlight, either partially or totally, and while the system is not able to supply AC power to load, then the additional energy is drawn from AC mains. AC mains power is converted to DC power by rectifiers to supply additional energy input to the battery. Diesel generator is also one of the choices in the absence of AC mains power. Both AC mains and diesel generator are non-renewable. Other renewable energy sources such as wind or hydro may also be used to expand the scope of hybrid SPV systems. Priority of charging starting from 1 to solar energy, followed by other sources, can be set by including electronic circuits in the input of battery bank. The success of the solar PV integration lies with proper planning and execution of the project. It needs accurate design of the complete plant, adequate knowledge of available technology, components variations, market provisions, manufacturers around, import essentials, logistics, manpower requirement, etc. supports the design team. PV system software is one such tool which simplifies the work of the design team to great extent. It even starts from analyzing solar irradiation location-wise and guides best approach for designing. A lot of financial decisions are taken based on the simulation report which is given as an output by the software. PV system software is designed to be used by architects, engineers and researchers. It is also a very useful educative tool. It includes a detailed contextual help menu that explains the procedures and models that are used and offers a user-friendly approach with a guide to develop a project. PV system can import material data as well as personal data from many different sources. PV system presents results in the form of a full report, specific graphs and tables, and data can be exported for use in other software. The system design is based on a quick and simple procedure. Specify the desired power or available area. Choose the PV module from the internal database. Choose the inverter from the internal database and PV system will propose an array or system configuration that allows you to conduct a preliminary simulation. This software embeds a color-coded warning or errors messaging system. If there is a mismatch, issue, warning with your design, you will be warned within the proper frame. There are other software available over the internet similar to the above. We can select, purchase and use for designing the solar PV plant. Study the inverter wiring diagram and connect the components of the solar inverter. Ensure you have all the following tools and equipment. 12 volt DC or 230 volt AC normal inverter, solar panels 75 watts 2 numbers, charge controller, connecting wires, load bank, 12 volt 100 ampere hour battery and clamp meter. Wiring sequence are as follows. Wire the charge controller. Connect charge controller to battery. Connect battery to inverter. Connect panel to charge controller. Connect loads. Keep all MCB in off position and fuses removed for safety. Follow the testing sequence of the inverter and test the solar inverter in a similar way for normal load, full load and overload conditions. Record the observations.
We have reached the end of this session on Connect a solar panel 10 watts, solar charge controller 12 volts 10 ampere, solar battery 12 volts 100 ampere hours and a normal inverter and convert to a solar inverter. By now, you should be able to understand the fundamental principles and components of a solar panel, define the role and importance of inverters in solar energy systems, including their function of converting direct current DC from solar arrays to alternating current AC, describe different types of inverters and their usages, and understand the critical factors contributing to the success of solar PV integration projects.
A warm welcome to all inquisitive audience. Today we are going to have brainstorming session on GRIHA, that is Green Rating for Integrated Habitat Assessment. Let's start with the session. The sequence of our presentation would be, first would be introduction, then green buildings overview, that is history, how green rating has come into current use, different types of